right, let's get started with 2.4, variation. And so our first objective here is going to be construct a model using direct variation. And what direct variation means is that if one variable changes, the other variable changes in the same direction. So if y goes up, then x goes up. Okay? If x was to go down, then y would go down as well. All right, so you're going to have a positive value for k as long as we have a positive direct variation. You could also have a negative direct variation coming down like that, whereas x increases, y would decrease. But as long as k is positive, you're going to have a positive slope going up. All right, so let's keep that equation, y equals kx, and look at a problem here. So the monthly mortgage payment on a mortgage varies directly, so there's our equation for direct variation, with the amount borrowed b. So right away, let's go ahead and say p equals some amount k, and then b. So we have our variables lined up. If the monthly payment on a 30-year mortgage is $7.40, all right, so payment, we've got payment already, 7.40, okay, equals k for every $1,000 borrowed. So the payment and the amount borrowed, we've got two variables, we plug them in, we're going to solve for k. So let's divide by 1,000. And we'll get k equal to, we'll move our decimal place 1, 2, 3 places. All right, so k is 0.0074. And so we have our direct variation equation of p equals 0.0074 b. All right, so that is the formula that relates the monthly payment p to the amount borrowed b. So now let's find the monthly payment when the amount borrowed is $200,000. So payment equals 0.0074 times 200,000. And so let's go 7, we can do this by hand. 7.4 times 2 is going to be 14.8. And we've got 5 zeros over here. We can move our decimal place 1, 2, 3, 4, 5. So your payment is going to be $1,480 on a mortgage of $200,000. All right, now that you've seen that, let's try problems 3 and problem 21. Okay, second objective, we're going to go with inverse variation. And what we have here is as x goes down, y goes up, but not in a straight line. All right, so as we get to the extremes, y will get, as y gets really, really big, x gets very, very small. We get in here, we never cross the line though. So the equation here for inverse variation, y equals k over x, and you can also use the equation k equals yx or xy to figure out what k is when we're solving. All right, so let's try one. The maximum weight W that can safely be supported by a 2 by 4 inch piece of pine varies inversely, so pause right there. W equals K over the length. All right, so the weight is inversely proportional to the length. Experiments indicate that the maximum weight that a 10-foot long, so K over 10, piece of pine can support is 500 pounds. So right away, let's solve for k. We're going to multiply by 10. K is 5,000. Write a general formula relating the maximum weight to the length would be W equals 5,000 over L. There's our general formula. Let's go ahead and find the maximum weight that can safely be supported by a length of 25 feet. So W equals 5,000 divided by 25. 25 goes into 104 times, and so 5,000 divided by 100 would be 50. 50 times 4 is going to be 200. So if you have a 25-foot long piece of pine, you can support 200 pounds. And if you have a 10-foot long piece of pine, you can support 500 pounds, which makes sense. If you have a much longer board, it's going to have a lot more stress in the middle as you walk on it. So, and that's what we said on the last slide. As one goes up, the other goes down. As the length went up, the weight it could support went down. All right, now that you've seen that one, see if you can do problem 31. Okay, so we'll put these together now for joint and or combined variation. And so what we're going to have here is y equals k x z or b or j, or it doesn't matter, q, multiple variables being multiplied together. So let's see if we can write some equations. No numbers here, just see if we can write it. The loss of heat through a wall, okay, so how about L for loss of heat, varies jointly, so equals K. What are the things we're going to vary jointly with? The area of the wall, A, and the difference between the inside and the outside temperatures. So temperature inside minus temperature outside. All right, so that's the word difference right here, and we're multiplying the rest of them. How about we vary inversely with the thickness of the wall? So the loss of heat varies inversely, so K over the thickness of the wall. How about thickness? TH, since I already used T up here. Okay? All right, so that would be the inverse variation equation. This would be our joint equation. Now that we've seen an example, let's see if we can do one using numbers. The force F of the wind, force, is going to vary jointly, so K, with the area, A, and the square of the speed of the wind, so V squared. A wind of 30 miles per hour, speed, 30 squared, is blowing on a window measuring 4 by 5 feet. 4 by 5 is 20. Okay, we're multiplying these all together. And that produces a force of 150 pounds. All right, so 150 equals K, and 20 times 900. And so we'll divide this, 150, divided by 2 times 9 is 18 with 3 zeros, equals K. And if we put that into our calculators, we're going to get let's see, where did my calculator go? .00833. Oh. Sorry about that. I'll keep going. Lost it. Come back. There you are. And where'd the calculator go? There we go. Wow, this doesn't want to cooperate at all. Sorry about that. .0. Well, you are just not cooperating. See if we can get this back. Sorry about that. Pointer options. There we go. .0833. I think that was what we had. Nope, extra 0 in there. .00833. All right, so what is the force on a window measuring 3 by 4 feet? So let's solve this. Force equals, we know our K now, .00833. 3's are repeating. The area is going to be 12, 3 by 4. And the wind is 50, so we're going to square that. Let's plug it all in and see what we get. So we're going to have .833 times 12 times 50 squared. And our force is going to be 250 pounds is our unit. All right, last one for you. You're doing problem 39. Any questions? Let's make sure we go over them in class. Good luck.